Hello, this is Matt Wright, and I'm here to talk to you today about the electric field. So let's start with something that you've known for a long time. If I have a positive charge and a negative charge, right, they are going to attract one another, right? But if I have a positive charge and another positive charge, they're going to be repulsive, right? We learned that when we were in like second grade and we first learned about charges and the basics of the universe. Okay, so we learned that their interaction went something like the following. That there would be some force equal to some constant, right, times Q1, Q2, divided by R squared, right, times R hat. All right, so remember that R hat always points away, and minus R hat points toward. Okay. So if both of these are positive, right, R hat is going to point away. If this one's positive and that one's negative, that's going to make this term negative. Actually, you're going to have a positive times a negative. You're going to get the negative R hat, which means toward. All right, this number here, epsilon naught, this is a super important number. The permeability of free space, 8.85 times 10 to the minus 12. And its SI units are Coulomb squared divided by Newton meters squared. Okay? We measure the units of the charge in coulombs, right? And then, of course, the SI units for the separation between them is in units of the meters. So this is Coulomb's law, right? And we've learned about this. Again, you probably learned about this in first year physics, and you probably learned about this in middle school, right? This is some pretty basic stuff. All right, now let's apply this to slightly more complicated systems. All right, the first thing that we're going to do in E&M is we are going to make an approximation. We are going to say, we're going to work with electrostatics. Electrostatics. All right, what that means is that I'm going to have a bunch of charges, okay, that are arranged some way. They're arranged in some way. And even though there's interactions between them, we are going to say they are fixed. Meaning they don't move. The thing I always like to say in class is they're held in place by the hand of God. Listen, I'm not trying to make a joke or anything there, right? They want to move, right? And we'll talk about that in chapter 7 and beyond. But for the first approximation of physics, we start where we hold these in place, where they're held. You can imagine like driving a stick through that charge, so the charge can't move. It's held there. And then we take another charge here, and we call it the test charge. Right? We make the test charge positive. It could have been made negative. Don't get too hung up on that. But basically, we can move this test charge wherever we want. Test charge could be here, 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 or there, anywhere, right? So then the idea is to figure out what the force would be on this mythical test charge, right? We're going to find its force field, right? Right, so, but we do a little bit of work to get it into something that is charge independent. We call the electric field. So what do I mean by that? Well, we're going to take out the charge of the test charge out of the summation, and we're going to get some new quantity called the electric field. So what does that look like? Well, if I have that test charge there, it feels a force from that charge here. So that you get a Coulomb's law, 1 over 4 pi epsilon naught. We'll call this charge 1. Is going to be charge 1, charge test, over R1 squared, R hat 1. Right? But there's charge 2 over here. Right? R2, Q2. And there's going to get a little push from that as well. It's going to be 1 over 4 pi epsilon naught Q2 Q test over R2 squared, R2 hat. And then there's going to be another one here from charge 3. So in order to figure them out, I got to add up the push from each of these things. In fact, that has a name. It's called the principle of superposition. I am just going to add them. I'm going to say the total force, force net, is equal to 1 over 4 pi epsilon naught Q1 Q test over R1 squared, R1 hat, plus 1 over 4 pi epsilon naught Q2, QT over R2 squared, R2 hat, plus dot, dot, dot. And I get each point. It's not just the closest one, because I also, here I'm going to have Q4. I got to include a term for that. Here I'm going to have Q5, right? So I'm going to have a bunch of terms in this sum. Basically, how this guy interacts separately with this charge, with that charge, with this charge, with that charge, with this charge. So in this case, I would have a sum of 5 terms. Now remember the approximation, the electrostatics approximation. These 5 charges are held in place, not moving. This test charge is going to sample what the force would be at any spot around these charges. So once I calculate that, I can determine what a force would be if I did happen to put a charge at that location. All right, so we made a choice. We take the test charge and we factor it out. So we get Q test charge, 1 over 4 pi epsilon naught, and then we have Q1, R1 squared, R hat 1 plus Q2, R2 squared, R2 hat, and so on. So what we do is we call this now, this thing right here, we call this the electric field, and we give it a value E, right? And that basically tells us the force, right? The force is equal to QE. So once I know what my test charge is, what the actual charge is of that thing, I can put it in here and put this electric field, which has all this information in there, and it will tell me what the force is on my particle. So what we really care about in electrostatics is determining what the electric field is. Once we know what the electric field is, then we're in business. we can know the force, and we know how this test charge is going to interact with the world. All right, let's dive in a little bit deeper. Okay, so the electric field is equal to 1 over 4 pi epsilon naught. And what we're going to do is we're going to say that this is times the sum of Qi divided by Ri squared, Ri hat, where this is going to be I equals 1 to how many particles I have in my system, right? Where this is the distance between the particles, between the test charge and that particle you're trying to find. And this here is the unit vector, right? It's the direction along which that vector would point. Okay, so this is basically doing what we did just a moment ago, but in a little bit fancier notation. So we're going to give this a name. We're gonna go ahead and make this script R. We're going to draw it like that, right? It's script R, but we draw it kind of like in a cursive-y way, right? So this is going to look something like right, where now I have this script R in there for the R squared. And the script R really means the distance between the charge that you're looking at and the point where the test charge is located at, right? So we're going to have a whole video on that because that's some complicated stuff. We really want to think about that in a deeper way. But now that we have this, we could say, well, wait a minute. What if n is really large? Right? What if it's really big? And what if this Q is really small? Okay. So if I have a lot of, if I'm summing over lots of pieces and this is really small, I can rewrite this in the following way. dq, and while this looks like a Riemann sum, this can become an integral. So 1 over 4 pi epsilon naught, the integral of now dq over rho squared over script r squared, script r hat, where now the script r becomes a function of the variables x, y, and z, right? Okay. So now, in order to determine this, I can just do this integral. So I can take some tricks and think about how Q depends on the volume. We can use something called the charge density, right? So rho, the charge density, is equal to Q over V, right? If it's completely uniform. But if I take a small chunk of volume, then I could say that it is uniform over that small chunk, right? It may change outside of the chunk, but in that chunk, it's pretty much uniform. So the density could become dq dv, which I can write now my charge distribution as rho dv. So I can write my, by cross multiplying, I can write my dq is equal to rho dv. So then my electric field becomes 1 over 4 pi epsilon naught, the integral of the charge distribution, which is a function of x prime, y prime, z prime, divided by script r squared, which is a function of x prime, y prime, z prime, x, y, z, times script r hat, which is a function of x prime, y prime, z prime, x, y, z. Now, times the volume, which is dx prime, dy prime, dz prime. Right, so all I did was I took my dq here, right, and I plugged in v dv, right, or sorry, rho dv. My rho is here, and my dv is here, right? It's a volume element, dx, dy, dz. So now there's a lot going on with, I have two coordinates in there. What am I talking about? What am I talking about when I have two coordinates? Well, the x prime, y prime, z prime, these are the location of the charges. Okay? They're the location of the charges, and these are the location of test charge. So that's the location of the charge you're looking for. We'll do more on this.